It takes that light through the solar panels. The star would slowly disappear from a, quote, a regular looking star and would ultimately appear as a red glow in your infrared telescopes. So there was a recent study in a peer-reviewed journal, the Monthly Notices of the Royal Astronomical Society, one of the more respected journals in the world, of a study that's just simply looking for these red glowing blobs in the galaxy, in the pre-existing data that's already out there. Didn't even have to design a telescope for this. The telescopes are already bringing in the data. They're just asking a different question on those images. So out of a sample of millions of stars, they found 7 candidates that might be one of these type 2 civilizations.
So, why would a civilization so far beyond us advertise itself not with bright stars, but with a faint, uniform warmth? The answer begins with thermodynamics. You can capture light in any clever contraption you want, a Dyson swarm of orbiting collectors, a lattice of habitats, but you cannot use energy without producing waste heat. A sun-like star radiates at about 5,800 Kelvin, peaking in visible light. If you intercept a large fraction of that light and do anything useful with it, compute, live, think, you must re-radiate almost all of it at a much lower temperature, a few hundred Kelvin, which shifts the peak into the mid-infrared. The Stefan-Boltzmann law guarantees that to dispose of the same power at a lower temperature, you need a larger surface area, naturally creating big, cool shells or swarms that glow like a warm fog at 10 microns. That spectral shape, starlight missing and the optical, reappearing as thermal infrared, isn't an artistic flourish, it's a thermodynamic invoice. Resolution. If stellar-scale engineering exists, its unavoidable signature is waste heat glowing in the infrared. But couldn't nature fake that glow? Absolutely. And that's why the search is hard and interesting. Thick dust cocoons around young stars, outflows from dying red giants, and entire dusty galaxies all glow warmly. Fortunately, dust and engineering leave different fingerprints. Dust grains show strong spectral features. Silicate bumps around 10 and 18 microns, polycyclic aromatic hydrocarbons lighting up at 6 to 12 microns. A spherical reprocessor built by engineers would be closer to a smooth blackbody. Disks of dust are flattened and often clumpy. An engineered swarm could be far more isotropic. Natural sources often show characteristic variability or outflows. Engineered systems should be stable on human timescales. Parallax and proper motion from precise astrometry tell you whether you're looking at a nearby star or a distant galaxy masquerading as a point source. Color diagrams from all-sky infrared surveys identify populations with distinct thermal ratios. Extreme outliers that lack dust features and have stellar distances are rare. Resolution. Many natural warm objects exist, but multi-wavelength spectra, geometry, and kinematics let us separate most imposters from credible techno-signatures. If such a beacon turned out to be engineered, what would it teach us about the trajectory of intelligence? It would reveal that the physics of information and heat management scales all the way up to civilization. Landauer's principle says each bit erased costs at least kT-ln2 of heat. Running colder lets you compute more efficiently. So, a civilization that wants maximal computation per watt will spread out, lower operating temperatures, and favor massive radiators. Precisely the conditions that glow in the mid-infrared. The economics of growth pushes the same way. Even modest exponential demand saturates planets quickly. Swarms harvesting a star's luminosity become rational, not extravagant. The raw materials are available. Disassembling a single Mercury-sized body provides enough surface area as thin films to intercept a star's light. Orbital mechanics and self-replicating factories reduce the time from centuries to millennia, cosmically brief. Communication across a swarm is bounded by light speed, so architectures become local and distributed, consistent with steady, uniform heat. Resolution. A confirmed infrared beacon would show that thermodynamics and scalability channel advanced intelligence toward large, cold, distributed infrastructures that look exactly like efficient, warm emitters. So, why look for them now, with imperfect tools and long odds? Because science advances by turning vague wonder into testable constraints. Existing sky surveys already sample the infrared sky with millions of sources. The trick is not building new instruments first, but asking sharper questions of the data we have and then targeting the survivors with precision spectroscopy and parallax. If no credible object survives those tests in our galaxy, we learn something real. Either star-encompassing engineering is rare here and now, or its lifetimes are short, or its designs are colder and subtler than our current sensitivity. Each outcome narrows the space of possibilities. If one object survives and passes every naturality test, we gain a fact of staggering consequence grounded in measured spectra, not stories. And there's a mirror held up to us. Our own energy use ultimately heats our environment. Every watt we burn, regardless of source, ends as heat. Learning to recognize waste heat across light years teaches us to measure and manage it at home. Resolution: we search now because the act of defining, ruling out, or confirming infrared beacons transforms speculation into knowledge and orients both our cosmic expectations and our earthly responsibilities. Like if this was interesting, and hit the subscribe for more.